All right, what we're going to look at now is chapter 19, which is about vibrations and waves. And so the first part, we're going to look at the vibration of a pendulum, wave descriptions, and wave speed. So waves occur when there's a disturbance in matter. And so you knock on wood, and what happens is that the wave from knocking, say do it on your desk, will emanate out, it reaches the edge of the table and bounces back. And so energy emanates from that disturbance. It also, of course, makes a sound where the energy goes out into the air. Anyway, so wave motion in matter transfers energy. So energy is carried by the wave. There are lots of different kinds of waves. There are ocean waves, sound waves, electromagnetic waves, and there's seismic or earthquake waves or shock waves. Also, we call them in the air. So anyway, there are lots of different kinds of waves that we'll be talking about. Okay, now we say that waves transfer energy in a variety of what are called mediums. Mediums is the material that it's in. So water waves are, of course, in a liquid, and earthquake waves move through the solid earth. Sound waves travel through the air, which is a gas. Electromagnetic waves don't actually need a medium except the vacuum of space, which is actually more complex than it sounds. But yes, they don't actually need any materials except empty space. So the sun could reach you from 93 million miles away. That sunlight reaches you here on Earth after traveling through 93 million miles of vacuum. Now, another thing is that the waveform is in motion, but not the matter. That's sort of a quote from your book. It's not entirely, the matter does move, but it doesn't move in the direction necessarily of the wave. So when you're in the water, if you're out waiting for a wave to come, you're out playing in the out a little deeper beyond the break of the waves in a lake or something, or the ocean. What happens is that you just basically go up and down. So your motion is in an up and down motion, a little bit of a circle, but you don't necessarily get pushed forward and travel with the wave. Only when the wave actually meets its breaking point does the energy change such that it actually carries the matter forward with it. So that's when you would mount your surfboard and you would be up on top of the wave. This shows the energy in waves that was put out by the 2011 Honshu earthquake and tsunami in Japan. Terrible earthquake, killed more than 10,000 people because of the tsunamis, the waves that were generated. So, so there's a chart over here. You can see black is higher waves, and in fact, black would be greater than 2.5 meters, so greater than 5-foot waves. Anyway, and so yes, very black there along the coastline. That's where they got most of the energy. And then as the wave energy spreads out, then you see it gets less and less in most places. So when it reached Hawaii, it was still slightly red there. And then there's this interesting channel that carries energy over towards the city called Crescent City, which gets hit by tsunami energy more than other places. It got hit when Alaska had an earthquake. There's just kind of this channel that carries energy over there. Anyway, the underwater channel. But anyway, that's the idea. The energy is carried by waves. Now, the disturbance might be a single pulse. You might just knock once on wood, or it might be more periodic, like a guitar string that comes back over and over again, oscillating, right? So guitars, and this is not in tune, so any musicians out there, don't. I know it's not tuned. Okay, so anyway, so sorry to make your nerves jangle. Makes mine jangle. Anyway, but the idea is that string keeps vibrating up and down for a while. Okay, now Galileo, as I've said, he's the one who discovered the relationship between a pendulum's period, the time that it takes for one complete swing, and its length, right? So you guys did that experiment a while ago where you figured out that mass didn't matter very much to a pendulum's period, and also the angle that you hold it out at, that didn't matter. But what did matter was the length of the string. And so that is what's important. And so anyway, but Galileo noticed what we would call periodic motion, of course. The pendulum keeps going back and forth and back and forth. And that the time or period for one oscillation was consistent, even when the angle changed, because as the pendulum might lose energy, the angle gets less, but the period actually stayed the same, which was pretty amazing. So there's this picture in your book of this science museum demo, which is called fading motion. And so what it is there's actually a cone hooked to this broomstick, and so you put sand in there, and when it goes back and forth, it lays down a pattern of sand. If you start this belt moving, then what happens is that you get to see the beautiful sine wave pattern that is produced as the motion of the belt carries it past the sand. Okay, so anyway, so what happens is, why is this called fading motion, is that over time the amplitude of the wave gets less. Now amplitude refers to how high it is. Okay, so the height of the wave, and that relates to energy. So as friction takes away the energy of the cone, then gradually the wave would get shorter. But the time between peaks and troughs would actually stay the same. That would be the period. And that stays the same. Okay, so terminology is important for understanding or talking about wave motion. So we've already talked about a few things here. Crests are the high point of the wave, or being an engineer, I usually call them peaks too. Peaks is another way to talk about them. Okay, and troughs are the low points of the wave. And the wavelength can be measured between two peaks or two troughs that are consecutive, or it can be measured from anywhere along the wave, as long as you start with the wave motion, for instance, going up here like this, as long as you get to that same point on the next wave. Okay, so you don't want to stop here because you're on the wave, but it's not one complete cycle. So the wavelength is the distance of one complete wave or one complete cycle, and you can measure it crest to crest or from any 2 points that are in the same spot. Now, another thing here is what's called amplitude. Oh, and by the way, wavelength is measured in meters usually, or centimeters. The symbol for wavelength is this upside down Y thing, which is called lambda. Okay, so it's the Greek letter lambda. It's easy to draw. Just draw it as some sort of scrolly Y thing upside down. And we had to use a Greek letter because we had too many W's, right? We've already got work, we've got watts, we've got weight. So lambda is the symbol for wavelength. Okay, now amplitude. Amplitude is how high the wave is. But for scientists, we measure amplitude from the equilibrium position. So we're looking for the maximum displacement of the wave from its equilibrium position. So think about how this wave here started. This is a mass on a spring. So the mass started in this location, and then it was pulled down, and then it's released, and it bobs up and down. Okay, so it bobs down this far and up this far. So the maximum displacement is from that initial starting point where it was at rest. That's what's its equilibrium position. So amplitude, you can see, is just measured from the center line to the crest, or from the center line to the trough. Those should be equal. And that's not how people measure ocean waves, as they're just out on the ocean. They don't try to find an equilibrium point. They'll just say, well, this wave is from here to here. That's 8 feet. That's a big wave. But a scientist would say, no, no, that's only 4 feet, right? 4 feet up, 4 feet down. Okay, so anyway, so not all scientists, probably ocean scientists just call them 8-foot waves. But yes, but in the lab, where we're often not doing water, we're doing other oscillations, we definitely measure from that equilibrium position. Okay, so amplitude is represented by the letter A. Usually we measure it in meters also, or centimeters. And it is related to the energy. The energy transmitted by the wave is directly proportional to the amplitude squared. So if we had a 4-foot wave, right, and we square that, that would be 16. If we had a 5-foot amplitude wave and we squared it, that would be 25. So we just made the wave get a little bit higher, but you can see the energy is going to be much greater for every foot. And if we double the height of a wave, so from 4 it goes to 8, 8 squared is 64. Doubling the wave height would make 4 times as much energy. Okay, so energy is proportional to the amplitude squared. Okay, so another way that we talk about waves is we talk about frequency and period. So we've already talked about period. That's the time it takes for a complete cycle of a wave, or for it to travel a distance of one wavelength. So to go one wavelength, it takes, if it's a 3-second period, that's between peak to peak, then that means it takes 3 seconds for the wave to travel one wavelength in that time. Okay, now frequency is the number of oscillations per cycles. So usually we measure that in hertz, so cycles per second. But of course we can measure frequency like we talked about in the rotational chapter. We can RPMs, rotations per minute, cycles per second is hertz. But there are other units that people use, like radians per second, talk about angular frequency. So those are actually related to this too. So rotation can be related to frequency, but we're not going to do it in this chapter. Okay, so anyway, now one thing is that 1 hertz is 1 cycle per second. And the period is basically the time for 1 cycle. So that's seconds per cycle. So you can see that these are actually upside down from each other. They're inverted. cycles per second, seconds per cycle. So one thing is that the period and the frequency are related. The frequency is 1 over the period, or period is 1 over the frequency. Both works both ways. So if we have a frequency that's 4 hertz, then the period is going to be 1 over that, 1/4 of a second. So they're inversely proportional. One goes up, the other one goes down. Okay, so here is our 2 example waves. One has a frequency of 4 hertz, the other one has a frequency of 8 hertz. Now they're moving at the same speed, so they move the same distance in the same time of 1 second. You can see, though, that one achieved 4 waves in 1 second, and the other one achieved 8 waves in 1 second. And you can see that that makes their periods different. One takes a 1/4 of a second for each wave, right? So the 1/4 of a second. The other one manages to squeeze a whole wave into 1/8 of a second. Okay, now another thing you might notice is the wavelengths are different. The wavelength for the 4 hertz one is longer than the wavelength for the 8 hertz wave. And this is something that's going to be a relationship that you're going to see over and over again. If waves are traveling at the same speed, then as the frequency goes up, the wavelength goes down. So that's an important relationship to have in your brain. And that's supposed to be a wavelength. The pin's not cooperating. There we go. Okay, so frequency up, wavelength down, and vice versa. Frequency goes down, wavelength goes up. So when I play a guitar string, low frequency, higher frequency, higher frequency. Now, if these are all under the same tension, which they probably aren't, that would mean the waves would travel at the same speed, maybe. And so the idea is that the higher pitch would have a shorter wavelength. Okay, now for guitar, actually, there's something wrong with that. We'll talk about that in a minute. But in general, that's the idea. If you have musical instruments where the tension is the same, slide whistle, for instance. Well, the slide whistle, what you're doing is adjusting the chamber length, which adjusts the length of the wave. So when I pull the slide whistle in, right? When it's longer, that's a longer wavelength, lower pitch. When it's shorter, higher pitch, because there's a shorter wavelength. Okay, so in this case, I'm able to change the wavelength with the slide whistle, and that's a trombone, basically. Okay, so now wave speed describes how fast the disturbance moves through the medium. And since speed is distance divided by time, remember our old formulas, wavelength is a distance, period is a time. So this formula can be used to find the velocity. However, usually when we're, working with sound, we usually refer to the frequencies by, we refer to the waves by their frequency, not their period. So like this tuning fork is not marked with the period, it's marked with the frequency, 256 hertz. That's middle C. So the thing is that usually we use this formula. Since period and frequency are related, then I can just substitute 1 over the period is the frequency. And this equation we're going to be using a lot. This is the main equation you'll need for this chapter and for the chapter on light. Okay, so this chapter, the next chapter, and the next chapter. So the next 3 chapters are on sound, and then we'll have 3 chapters on light. And they all use the same equation. Velocity is wavelength times frequency. So it's a very, very useful equation. Now, the wave speed depends on the material, the density, the temperature, and the tension. So one of the things about a guitar is it's an excellent thing for studying that. Guitars have strings that are not all the same. So some strings are thicker and some are thinner. And that's referred to as string density. Okay, then it can be different materials too, like is it a nylon guitar string or a metal guitar string like this? So material density, the temperature, which is why people always have to tune their musical instruments because they take them from one place to another. The temperature changes, that changes the length of the string, changes the tension. Because tension is the other thing. Of course, you tune a guitar or untune a guitar, often is what I do, by adjusting the tension, right? Okay, so you adjust the tension. And so anyway, so a guitar is an excellent one because it actually has different density of strings. So do pianos. Okay, so that way they can have the string length be pretty much all the same. Okay, and the tension pretty much all the same because you don't want one part of the guitar being pulled more than another on one side. So anyway, so they try to keep the tension about the same by changing the string density, by having wound guitar strings. And more mass means more inertia. More inertia means it moves more slowly as it tries to vibrate. And that makes a deeper sound. So the guitar bass strings are thicker. Okay, so let's use this equation. Let's look at a guitar. So here's the wave. So let's find out what the wave speed is on a guitar string. And so let's just pick a string. Let's see. All right, so let's pick the B string. The frequency, if it was tuned, would be 246.9 hertz. So let's throw that in here. Frequency, 246.94 hertz. Okay, now we need the wavelength. Well, one of the things about the guitar and many other musical instruments is they play in what's called the fundamental mode. And in that case, the guitar string is just going up and down, like a rope, a jump rope. And so one of those things leads to the wavelength is not from here to here. So from the frets down here. Instead, the length of the wave, that's just going up and down, up and down. But a full wavelength, you'd have to have an up and a down, right? So what happens is that the wavelength is actually 2 times the length of the string. So what we have to do is measure the length of the guitar string to figure out this problem. Okay, so measuring my guitar string. It's around 65 centimeters long. Okay, so since the length is 65 centimeters, then I'm going to have 2 times 65 centimeters, or 0.65 meters, which is going to be 1.3 meters for the wavelength. And now we can figure out what the velocity is. We're going to have the wavelength, 1.3 meters, times the frequency, 246.94 hertz, if it was in tune, which it's not. And so I would get 321 meters per second. Okay, so remember that musical instruments play in the fundamental, and that the wavelength is going to be 2 times the length of the string, because that will come up in some of your homework problems and test problems. Okay, let's keep going then. Now, the other kind of problem that you get involves another equation, which are echo problems. And you get more of those in the next chapter. But basically, the equation that you're going to use is distance equals velocity times time. And so that's an equation that you already know. But what you're saying is that the wave has a velocity. And usually the velocity of sound at room temperature is around 340 meters per second. And so we're going to use that as our standard velocity for homework problems. It's a little closer to 343. So I think that's what's written on your equation sheet, but either will be fine. And so that would be at about 20 degrees Celsius. So this has a horn honking, and that reflects off a cliff, and it comes back, and you hear the echo. And it takes 2.5 seconds for that to happen. So the thing is, I can use the velocity, 340 meters per second. And then the question is, well, what time do I use to get the distance? Okay, because if I use the 2.5 seconds as is, that's really the time for there and back, right? So what I can do is divide by 2 now and say, okay, well, it was 1.25 seconds there. It's going to take 1.25 seconds to return. And so that is what the time is. The other way is to go ahead and use the 2.5 seconds, but realize that you've got the round trip distance and that you're going to have to correct that at some point. Because it's too long. It's double the actual question. Okay, so now that we've got the right time, we can go 340 times 1.25 and get 425 meters, which is pretty far away. Okay, because it was a pretty long time. Anyway, so that's the idea, is that for echo problems, remember that usually there's a doubling of the time or doubling of the distance. You'll have like some bat ones in the next, bats chirp and the echo comes back from the side of a cave. So anyway, so you're going to have problems like that in the future. So anyway, those are basically the 2 equations that you need for this chapter and for the light chapter. Are just those 2 basic equations. Velocity is wavelength times frequency. Distance is velocity times time. Now, wave speed depends on the material and the type of wave. So electromagnetic waves, which you can remember, right? Electromagnetic is EM. Okay, they all move at the same speed in a vacuum or in air Close enough. It's 3 times 10 to the 8th meters per second. Very fast. Now, water waves actually depend on a bunch of stuff. The speed. They could go. I've written just a number here as an estimate, but I wrote 0.1 to 50 meters per second, but they have been found to go at over 200 miles per hour. So I need to update that to 100. But the speed depends on the depth, the wavelength, strangely enough, and the density of the water. Is it salt water or fresh water? And those would be waves on the surface of the water. Waves inside are usually sort of vibrational waves. And and water waves, you can measure the wavelength from crest to crest. That's odd. Oh, okay, never mind. Okay, so anyway, earthquake waves we'll talk about later. All right, so that's actually the end of this talk. So we're going to turn this off and go to part 2. So waves travel at different speeds.